Stretching the limits. The science behind the elasticity of rubber bands. Introduction. Rubber bands, those humble loops of elastic material, possess a remarkable property: stretchability. The science behind the stretching of rubber bands lies in the unique molecular structure of rubber, specifically its polymer chains. Let's unravel the intricacies of this elasticity and explore the scientific principles that allow rubber bands to stretch and snap back into shape. 1. Polymer structure of rubber. Polymer chains. Rubber is a polymer, meaning it is composed of long chains of repeating molecular units called monomers. In the case of rubber, the monomer is isoprene. These long chains, known as polymer chains, are what give rubber its unique properties. Cross-linking. Within the polymer chains of rubber, there are cross-links, chemical bonds that connect adjacent chains. These cross-links create a network-like structure, contributing to the elasticity of rubber. The more cross-links there are, the more elastic and resilient the rubber becomes. 2. Entropy and entanglement. Random arrangement. In its natural state, rubber is characterized by a somewhat random arrangement of its polymer chains. This random arrangement allows for movement and flexibility within the material. Entropy and disorder. When a rubber band is stretched, the polymer chains align in the direction of the stretch. This alignment reduces the disorder, or entropy, of the system. According to the laws of thermodynamics, systems tend to move towards states of higher disorder. In the case of a stretched rubber band, releasing the stretch allows the chains to return to their more disordered, relaxed state. 3. Van der Waals forces. Intermolecular forces. The elasticity of rubber is also influenced by intermolecular forces, specifically van der Waals forces. These forces arise due to the interactions between molecules or atoms that are in close proximity. Stretching and alignment. As a rubber band is stretched, the polymer chains align, and the van der Waals forces come into play. These forces act to pull the chains back towards each other when the stretching force is released. The combination of alignment and intermolecular forces contributes to the rubber band's ability to return to its original shape. 4. Hysteresis. Energy dissipation. When a rubber band is stretched and then released, some of the energy put into stretching it is dissipated in the form of heat. This phenomenon is known as hysteresis. Hysteresis is a result of the internal friction between polymer chains as they slide past each other during stretching and relaxation. Temperature dependence. The amount of hysteresis is influenced by factors such as temperature. At higher temperatures, rubber bands tend to exhibit more hysteresis, meaning they dissipate more energy as heat during the stretching and relaxation process. 5. Practical applications. Elasticity in everyday objects. Understanding the science behind the stretching of rubber bands has practical applications in various fields. Rubber bands are widely used for their elasticity, from simple office supplies to complex industrial applications. The ability to stretch and return to their original shape makes rubber bands valuable in situations that require flexibility and resilience. Conclusion. The science behind the stretching of rubber bands is rooted in the molecular structure of rubber, specifically the arrangement of polymer chains and the forces that come into play during stretching and relaxation. The unique combination of entropy, intermolecular forces, and hysteresis allows rubber bands to exhibit their remarkable elastic properties. This simple yet fascinating science has not only made rubber bands indispensable in everyday life but also contributes to our understanding of the behavior of polymers and materials at the molecular level.